In this session, we're going to discuss graph, terminology, and special types of graphs. So specifically, again, some terminology about graph. We're going to discuss some special types of graph, and we're going to define what is bipartite graph and how we're going to derive a new graph from old, okay? And from new graph, we're going to create a new graph, okay? So now let's continue. Okay, so let's define first what is adjacent, what is neighborhood, and what is degree of vertex. If say adjacent, so these are vertices connected to a certain vertex. So it is called adjacent. And the collection of these adjacent or neighbor vertices is called neighborhood. And the number of edges that connects these neighbors, these adjacent vertices, is called degree of vertex. So for example, what are the degrees and neighborhoods of the vertices in the graph G and H? So by the way, if we're referring to the degree or number of edges between vertices, so we're going to use this notation, DEG refers to degree, and capital N means neighborhood. We are defining the different vertices connected to a certain vertex. Okay, so let's have graph G. So what is the degree of at A? So how many vertices connected to A? We have B and F, so we have 2 degrees at B. So B is connected to C, to F, to E, and to A. So we have 4. And for C, it is connected to B, F, E, and D. So we have 4. And for F, it is connected to A, B, C, and E. So we have 4. So the degrees for B, C, and F is 4. Okay. While for G, since it is not connected to any vertex, so the degree is 0. There's no edge connected to it. There's no vertex connected to it. Okay. So what is the neighbor of A naman? Okay, so what are the vertex connected to A, B, and F? So you're just going to write it to create a set. How about B? So it is connected to A, C, E, F. And for G, null since it is not connected to any. Okay, so that's vertices, okay, degrees of vertices, neighborhood, and neighbors or adjacent vertices. Okay, now through the degree of vertices, we could determine the number of edges in our graph through theorem number 1, which is called handshaking theorem. If G is equal to vertices edges is an undirected graph with M edges, then 2M is equal to summation of vertex, okay, summation of vertex degree at vertex. Okay, so you're just going to add all the degrees of each vertex, okay, and it is equivalent to 2m. So for example, so how many edges are there in a graph with 10 vertices of 6 degrees? So it means we have 6 degrees connection between vertices with all vertices. So knowing that, so we have the first vertex, we have 6 connection. Second, we have 6. We have for the third vertex, we have 6 connection until to 10th vertex, we have 6 connection or 6 edges. So basically, if we're going to add it, we have 60 or 6 times 10, we have 60. So using 60, just substitute it to our theorem. 2m is equal to summation of, okay, so 2m is equal to 60. So by solving for m, we have 30. So it means we have 30 edges for this type of graph that includes 10 vertices and have a degree of 6. Okay, but in case if we have graph has 5 vertices, okay, and we have degree of 3, we cannot use, okay, we cannot use theorem number 1. Okay, we cannot use theorem number 1 since 3 times 5 is odd. So if we're going to use the handshaking theorem, it will give us 7.5. And definitely there's no 0.5 edge. There's no half edge. Well, it should only have a whole number edge. Okay, so that's why it cannot be used if we have, okay, a summation of all, okay, all the okay, based on the 5 vertices and the degree. Okay, if we're going to add it, if we're going to have an odd number result, we cannot choose handshaking theorem. Okay, so don't forget that. We could only use it if the result is even. Okay, now let's have theorem number 2. An undirected graph has an even number of vertices of odd degree. Okay, so using handshaking, we could use handshaking for this, since anything multiplied to even number, even its odd number of degrees, it will yield even number. Okay, the result is even number. The product is even number. So for example, we have 4 vertices, and we have 3 degrees. Okay, 4 times 3, it's 12. So therefore, it's even. It will yield an even number. So therefore, we could use the handshaking theorem. Okay. Now, let's move on with the directed graph. We're going to count the number of edges going to and going out a certain vertex. Okay. So again, if you're referring to directed graph, the edges has direction. We have a start vertex and we have an end vertex. Okay, so don't forget that. Okay, so if you're talking about in degree of vertex, it means going to that vertex. Okay, this it is called in degree, going to. Okay, so this is the notation for in degree. So deg dash the vertex. And going out of the vertex, going to another vertex, we call it out degree of V or vertex. So this is the annotation for that, or the how do we denote it? Deg plus V. Okay. So for example, deg dash A. So it means going to A. How many edges going to A? So we have from E going to A, we have 1. And from A, we have a loop. So we have 2. So that's why in degree of a vertex A is 2. And how about in degree at vertex B? So how many going to vertex B? So we have coming from C, 1, coming from A, 2. So we have 2 here. And for F, where is F? It's here. There's no connection, or there's no edge connected to F. So therefore, it's 0. There's no in degree. Okay, now let's discuss the out degree, going out. So degree out at A. So we have going out from A, so going to C, so we have 1. Going out from A, going to E, we have 2. And going out from A, going to B, we have 3. And going out from A and going to A, so we have 4. And for going out at C, so we have 1. From C, going to C, we have 1. Going to B, we have 2. Okay, so that's out degree and in degree. Okay, again, in degree going to that vertex, out degree going to the another vertex. Okay, and we have this theorem number 3 that determines the number of edges. So let G equal to vertex and edges be a graph with directed edges. So the summation of edges is equal to the summation of vertex degree in degree at vertex V equal to the summation out degree at vertex V. So basically, okay, the number of edges for the out is equal to the in is equal to the number of edges if we're talking about directed edges. Okay, so now let's move on with the special types of simple graph. So we called complete graph on n vertices. So it means that all vertices are connected with each other. Okay, so that's a complete graph. So for example, we have one vertex. So this is a complete graph because one graph is connected to itself. Okay, how about two vertex? So two vertex connected by one edge is considered as complete graph. Three, okay, three vertex, okay, connected by three edges are considered as complete graph. And for the cave, four vertices, so they are all connected. So this is considered as complete graph. Okay, same as with this and this example. So again, complete graph means all vertices are connected with each other. Okay, and we also have the cycle C at n with W at n. So n means the number of vertex. So cycle, so this is considered a cycle if the vertex is greater than or equal to 3 and it forms a certain shape. Okay, so the connection, okay, so we only have two connections for each vertex. Okay, so for example, vertex 1, this is vertex 1, it is connected to vertex 2, vertex 3. And vertex 2 is connected to vertex 1 and vertex 3. So we only have two. For the four vertex, this is vertex 1, so connected to vertex 2, vertex 3. And for vertex 3, connected to vertex 2, vertex 1 rather, and then vertex 4. Okay, only two should be connected to one vertex. Okay, so that will be cycle CN. While for the wheel, the only difference between cycle is we have a connection. Okay, we have three connection, and the third connection will be the central connection of other edges. Okay, so for example here, so we have a central connection between the three. We have a central connection for the 4, for the 5, and for the 6. So that's a wheel. And that's the difference between cycle. Okay. And we also have n-dimensional hypercube. So we're in, okay, a graph with 2 raised to n vertex representing all bits of strings, all bit string of length n, where there's an edge between two vertex that differ in exactly 1 bit position lang. So 1 bit position or 1 bit ang nagbago is connected to that vertex. So for example, 0 is connected to 1. Okay, and then 1, 0 is connected to 1, 1. 1, 0 is connected to 0, 0, but 1, 0 is not connected to 0, 1 kasi dalawa ang nagbago. So it's like creating a gray code. Okay, so we could have this. Okay, so that's n-dimensional hypercube. And we also have special type of graph that is used in computer network. We have a star topology. If say star topology, we have a central connection between nodes, and we have ring topology. So our nodes or our vertices are connected in a circular manner, and we also have WN based topology, which is combination of star and ring topology. And we also have hypercube or mesh network for computer network. So that's one of the application of the different types of network or graph in a network. Okay, so now let's move on with bipartite graph. So bipartite graph, a simple graph G is a bipartite if V can be partitioned into two adjacent subset V1 and V2, such that every edge is connected at vertex in V1 and vertex in V2. In other words, there are no edges which connect two vertices in V1 or V2. So basically, we could divide our graph into two groups, okay, without any problem. So when we divide it, so the vertices, okay, the neighbor of that vertex will be on the other part of the on the second subset. Okay, so we have two subset. So the neighbor of one vertex will be on the next subset or on the second set. So that will be bipartite. In case if we don't get that, so it's not a bipartite. So for example, so we have this graph G. So we're going to start with A. So what are the adjacent to it? G and C. So G and C should be on the other graph when we divide it. Okay. So A will be on the first graph. G and C will be on the second graph. Okay. So we should be consistent with that. Okay. Now, so which are connected with G? A and D. So definitely A is in the first graph. So D will be in the second graph. So we're going to denote it as red. So how about D? Okay. So D is red. So all connected to it should be blue or on the second group. So C, initially it's on the second group, so correct. G is on the second group, which is correct. And F and E is connected to another group. It's on the second group, so which is somehow true. Now let's move on with E or with C. So now C, it is connected to A, B, and D. Definitely A and D in the first group, but how about B? It will be, it's not yet been grouped, so therefore it will be B on the first group. So based on our grouping, meron na bang grouping lahat? Yes. A, B, and D will be in the first group. Red group will be on the blue group or the second group. So that's how bipartite works. If we could separate it, that will be bipartite. Okay, so it means to add two disjoint subset, we could create a two disjoint subset from it. How about letter H? Graph H, can we do that? So for example, A. So A will be red, F will be F and B. Okay, but if we're going to consider B, A will be in the first group, correct? But how about F? Based on this should be in the first group. But F, based on the perception of B, it should be in the second group. So therefore, we cannot create a bipartite. Okay? Okay, let's have this example. Show that C6 is a bipartite. Okay? So let's denote this. This is 1, 2, 3, 4, 5, and 6. Okay. So this is 1. So anything connected to 1 will be on the second group, which is 2 and 6. So ito yon. So now let's move on with vertex 2. So vertex 2 is connected to vertex 1 and vertex 3. So vertex 3 will be part of the first group, correct. Vertex 1 is on the first group. Okay, now let's move with vertex 3. Okay, so vertex 3 connected to vertex 4. So vertex 4 is part of the second group. Vertex 2 is part of the second group. And then for vertex 4 is connected to vertex 5. So vertex 5 will be part of vertex of the first group. Okay, and then vertex 5. So to check, definitely vertex 4 is part of the second group. Vertex 6, based on our initial analysis with regards to vertex 5 should be in the second group. So in this, vertex 5 connected to vertex 6. So vertex 6 is part of the second group. So correct. So therefore, we could divide it into subgroup. So this graph 6 is correct. It is a bipartite. How about C3 graph? So first, this is vertex 1, vertex 2, vertex 3. Vertex 1 is on the first group and the other will be on the second group. But if we're going to consider vertex 2, vertex 1 is the first group, but based on vertex 2, vertex 3 should be on the first group. But based on vertex 1, it should be on the second group, so we have conflict. So therefore, this is not bipartite. Okay? If we have vertex that could be allocated on both, it is not considered as bipartite. It should be either first or second. Okay? Now let's move on the complete bipartite graph. Okay? If say a complete bipartite graph, graph KMN, okay, is a graph that has its vertex set partitioned into two subsets. Vertex 1 of size n and vertex 2 of size n, such that there is an edge from every vertex v1 to every vertex 2. So we have two groups, okay, which is M group vertex and M group vertex. So for example, we have graph K 2, 3. So it means the first two vertex, the first group will have two vertex, and the second group will have three vertex. Okay, so the first connected to each, we have three, and the second one, two, three. So that will be a complete vertex for this scenario. And for 3, 3, we have for the first group three vertex, and the second group we have three vertices. So each vertices first on the first group will be connected on the other vertices. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So therefore, it's a complete. Okay, all vertex of the first group is connected to the all vertex of the second group. That will be complete bipartite. So how about 3 and 5? So we have 5 connection for the first node for the first group. Second vertex will have 5 connection. Okay, and then third, same as with the 6. So that will be complete bipartite. Okay. Okay, so another example of bipartite graph and matching. So basically, this is intended for somehow for um, employee matching, for job matching. Okay, so we could do that. Job assignment. Okay, and marriage definitely on an island. It could be bipartite. Okay, and now let's discuss new graphs from old. We're going to derive a new graph from old. So if say defining a new graph from old, we're going to get the vertices and the connection of the old to create the new. So for example, we have this, okay? And we're going to derive all the connections, all some of the connection and some of the vertices from here to create this. As you can see, this graph is part of this, and it follows the connection of this. Same as with this, okay? So we call it a subgraph of the old, okay? Okay, so how about this? So we have two old new graph, and we want to merge it. So we're going to follow all the connection based on graph 1 and graph 2, and then we have the new graph. That will be the result. So for example, A is connected to B, so still on our new graph, it is connected to AB. Since this is connected with AB, so just copy it. So in here, D is not connected to B, but here, D is connected to B. So therefore, on the new graph, it will be part of the new graph. Okay, all connection from graph 1 and graph 2 will be merged to create the new graph. Okay, so that's union of two simple graph. Okay, so that's how we create new graphs. So create a subgraph based on the old graph. It should be part of the old graph. That's a subgraph. And new graph based on union of simple graphs. Okay, so that will be my last slide for this video presentation. Thank you for listening. If you have some question, kindly send me a message, please. Thank you. On the next video lecture, we're going to discuss representing graphs and graph isomorphism. Thank you.